Okay, continuing on with Chapter 13 problems related to cylindrical coordinates, we have a problem that says the pendulum bob has a mass m and is released from rest when theta equals 0 degrees. That means straight out. Determine the tension in the cord as a function of the angle of descent, theta. Neglect the size of the bob, so we will be treating it as a particle. And so we could work this in normal tangential coordinates, and then it would be no different than the swing problem that we saw in normal tangential coordinates. And we had to do some integration to get something about velocity at each point. So really the purpose of this problem is just to show you that integration done in cylindrical coordinates rather than normal tangential coordinates. And then the rest of it is a fairly simple F equal ma problem. Okay, so I've already written a few things on this diagram, noting that the radial direction unit vector is pointing straight out from the center as we would expect, and therefore the theta direction unit vector E theta would be pointing there. Let me zoom out a little bit so now that we can see the rest of this a little bit better on this screen. Okay, and so I've got a free body diagram for this bob showing the tension going in the negative radial direction. There's our radial unit vector, and we have gravity acting straight down. Here's our theta direction unit vector, and this angle is a measure of theta, and in this picture, in addition, this angle would be a measure of theta, if you find that helpful. Okay, now at any point, if we're going to sum forces and learn anything useful, okay, including this tension force, which we notice is always in the radial direction. It's also in the normal direction, but it's in the it's in the negative radial direction. We can learn something about this tension force by summing forces in the radial direction. Now, and setting equal to mass equal acceleration in the radial direction. Okay, looking at that, if we're going to deal with the radial direction acceleration, we're going to need to say something about r double dot, but that's easy. We're moving on a circle. Radius never changes. That term is 0. But we're also going to have to say something about r, which is a constant. That's easy. But theta dot. Theta dot is the angular velocity, which relates to the linear velocity very easily when we're traveling on a circle. So that's the angular velocity of this swing. And we're going to have to say something about the angular velocity as a function of theta, our position, if we're going to sum forces in the radial direction and set it equal to the acceleration term in the radial direction. So now that we know we're going to need theta dot, let's go deal with theta dot. Okay. In this particular problem, the radius quantity r is L, not a function of theta, equal constant. Therefore, r dot and r double dot are equal to 0. Now, converting between, and we're getting a little bit ahead of ourselves because this is going to be dealing with rotation of rigid bodies later. But V equal r omega, V equal L theta dot being angular velocity, sometimes called omega. So you're probably familiar with the V equal r omega idea from physics. And so the velocity of the bob is the radius times the derivative of theta with respect to time. And we're going to integrate an ADS equal VdV, a lot like to say something about velocity, so we can relate it back to theta dot. So we're going to do an ADS equal VdV integral, set up typically, where we want acceleration in the theta direction because the theta direction is also the tangent direction, and acceleration in the tangent direction, rate of change of speed. This is all conceptually just a touch complicated, and frankly I'm never going to ask you to do this on a test, but it's still worth seeing. Maybe you don't want to spend any time on it tonight studying for the first test. Come back and look at this particular piece a little bit later. Well, this VdV integral from starting velocity to final velocity, that's very straightforward. Okay, and if we have an ADS integral, this is going to have to be from starting position to final position. But what we're going to do is, since A depends on theta, then we are going to, in the end, in a moment, change that to d theta, very much as we did in the swing problem. So, having gone to the equation sheet just a moment ago, well, let's see, we didn't look at the A theta equation. The acceleration in the theta direction, which for this problem is also the tangent direction, is r theta double dot plus 2 r dot theta dot. Now, r never changes, therefore r dot is 0, so this whole term is 0, and we're left with r theta dot. That's what we say right here, that the acceleration into the theta direction is both terms, but that term goes to 0. Therefore, a theta is equal to L theta double dot. Okay, and jumping ahead just a little bit, but if I were going to say sum of forces in the theta direction is equal to mass times acceleration in the theta direction, then what are the sum of forces in the theta direction from this picture? And the answer is this force mg has a component in the theta direction of that amount, and that is going to be a cosine of theta term. So sum of forces in the theta, it's a little bit small, equals mass times a theta. The force is mg cosine theta is equal to m, but a theta we already said was L theta double dot. L theta double dot. Cancel the m's, and what we have is a theta, which happens to be L theta double dot, is also g cosine of theta. We're going to make that substitution here and say that the acceleration in the theta direction is g cosine of theta, and ds, since we're changing variable, needs to be written in terms of d theta, and ds is LD theta. The arc length of an arc segment is the radius times the angle through which the arc sweeps. So we'll change this into an LD theta, and we will now integrate from theta equals 0 to a dummy theta, and integrating from the v0, because we started from rest, to a dummy v. This quantity is going to give us a v squared over 2, and this quantity, when we integrate the cosine of theta, is going to give us a sine of theta. So this integral will give us 2gl sine of theta. But now, this integral will give us gl sine of theta. But we had v squared over 2 over here. We'll bring the 2 over to the other side and then take the square root, and we get that velocity is square root of 2gl sine of theta. Now, this one might look a little different because last time I think we had cosine of theta from the girl on the swing, but remember we measured the inside angle. Sorry, you can't see that. Remember we measured the inside angle for the girl on the swing, not the outside angle. Okay. Boy, I haven't been watching my screen well. I hope I scrolled down, but again, just to summarize, a theta is from the equation sheet L theta double dot, but from sum of forces equal mass times acceleration, the a theta is g cosine of theta when I've canceled the m's. That's the substitution I make. Integrate, get velocity, but back up here we said velocity is equal to L theta dot. Let's use that definition, which means theta dot is equal to v over L. So we're going to do theta dot equal v over L. Bringing 1 over L inside of here will be a 1 over L squared. Canceling that L up top, we'll leave 1 L in the bottom. So theta dot is this as a function of theta. And now we are ready to solve the true problem now that we know theta dot as a function of where we are. Because to find the rope force, looking back, we're going to sum forces in the radial direction, because the rope force only appears in the radial direction. and we'll also have a piece of gravity in that direction, and set it equal mass times acceleration in the radial direction. From the equation sheet, acceleration in the radial direction had two terms. That one with the derivative of r goes to 0 because r is a constant. So here's our acceleration in the radial direction. But our sum of forces, okay, so we're going to do a sum of forces in the radial direction that says tension in the negative radial direction, a piece of gravity in the positive radial direction equal mass times acceleration in the radial direction. Now, where does this term here come from? R theta dot squared. This comes from, well, first of all, R is equal to L. So this is really L theta dot squared. And from the previous page, theta dot is, let's scroll it, theta dot is that. Therefore, L theta dot squared will get rid of the square root, and it'll actually cancel the L. So from the previous page, AR was that. Setting sum of forces equal to acceleration in the radial direction, and we end up having rope tension is a function of theta. Solve for T, and so T is equal to 3 times mg times the sine of theta. Of course, this has the largest value of T when the sine of theta goes to 1, and the sine of theta goes to 1 when our angle is pi over 2. And so the maximum rope tension in this problem is 3 times the weight of the object at the bottom. Messy. You might need to think about it for about 20 minutes before you can absorb all this stuff. Bottom line is, maybe don't sweat it too much, because in just a moment the hero of chapter 14 is going to be working energy. We'll make all of this stuff totally unnecessary. But this does show that we at least have the means to solve these problems with only chapter 13, but this is a hard chapter 13 problem, and it turns out to be a very easy chapter 14 problem. All right, moving on. Let's look at a very traditional problem. Look at the diagram for just a few minutes, and then we'll read the problem statement. What we have is a slot that's in the vertical direction. We're going to place a ball in that slot, and that ball must therefore travel only along this vertical line. Now we also have half a fork, and we only need half of a fork because gravity is going to keep the ball in contact with this arm. And we're going to control the angle of this half fork, which will control the height of the ball, and the ball will always touch this arm and be in the slot. And so we're going to work this as a problem in cylindrical coordinates. Let's see what we're being asked to solve for. But here is our geometry, and we do know that 0.5 is the distance from the center of the coordinate system to the center of the slot. We're also told here that theta dot is 2 radians per second. Let's see what shows up in the problem statement. Okay. The particle has a mass of a ½ kilogram. It's confined to move along the smooth vertical slot due to the rotation of the arm. Determine the force of the rod on the particle and the normal force of the slot on the particle when theta goes to 30 degrees. The rod is rotating with a constant angular velocity, theta dot, 2 radians per second. Assume that the particle contacts only one side of the slot at any instant. That way we don't have to worry about friction on two sides or anything like that. So we're wanting to find the force between the rod and the ball. And that will be perpendicular to the rod, and that is in the E theta direction. We also want to find out the force between the ball and the slot, one direction or the other, and that's either going to be a force that's to the left or a force that is to the right, because pure left and right would be normal to this curve, which is called a straight line. The normal to a straight line is perpendicular to the straight line. Now, when the path is curved, it matters which direction our normal vector goes. When the path is a straight line, it doesn't matter which way we point our normal vector. Okay? But it does mean we're going to want to find the angle between the normal vector and these other things. So let's say that the normal is that way, which means we're going to want to find the angle between the tangent and everything else. And the tangent direction would be perpendicular to the path, and so this would be an E sub t, and this angle between radial and tangent is solvable. We will be summing forces at some point. That's going to be probably the easy part of the problem. And so let's take a look at a free body diagram. The forces that we have will be weight acting straight down. That's one force. We will have the force between the rod and the ball acting in the upward E theta direction. So that would be our second force. And then we're going to have a force between the ball and the slot, and we're going to draw it as a force to the right. We don't really necessarily know which way it's acting, although looking at the picture, it looks like we are driving with this arm, the ball against the left-hand surface, and if that's true, the left-hand surface will push the ball to the right. So that is probably the right direction. We don't have to get that right for this thing to actually give us the right answer, though. So that's force number 3. Got 3 different forces, and right now we could use that inverse tangent function to find the angle between the radial and the tangent. But this geometry is awfully easy because that's a straight line, and it's a straight vertical line. So this angle is theta. This is a 90 degree, therefore this one is equal to 90, and I'm going to put degree marks on that, minus theta, or it's pi over 2 radians minus theta. Let me move that where you can see that. This is our angle theta, just like that's our angle theta. Here is the tangent, so this angle is 90 minus theta, and this angle is theta, and this one is 90 minus theta, theta, 90 minus theta, etc., over and over again all the way around the circle. Okay, so free body diagram, we will be summing forces in maybe both directions. I think we're probably going to sum forces in both directions because we have 2 unknowns. We have that normal force and we have the friction force unknowns. It's probably going to take 2 equations solved simultaneously to solve for it. Now, in order to have any hope to do that, we're going to have to sum forces equal mass times acceleration in that direction, and we'll sum forces instead equal to mass times acceleration in the theta direction, which means we got to have all of these numbers to flesh out the radial direction acceleration, both terms, and to flesh out the theta direction acceleration, both terms. All right, to get these acceleration pieces from these numbers, which means finding these numbers, every bit of that is a chapter 12 piece. Right up to the point where we find values for these numbers and plug them in, that's chapter 12. Then chapter 13 becomes a sum of forces kind of problem. So let's go to the chapter 12 stuff. I need to zoom out a little bit more. Okay, now we need r of theta if we're going to make any progress, because we're going to need to take derivatives of this with respect to time. We were not given r of theta as an equation, but because this geometry always forms a triangle, okay, then we can say that this distance r is related to this angle theta and is related to that total distance of 0.5 meters, 0.5 meters, okay? And what we can do is say that this 0.5 is r times the cosine of the angle theta. Okay, so 0.5 equals r cosine of theta. Therefore, r of theta is equal to 0.5 over cosine theta. 0.5 over cosine of theta, and this is an r of theta equation. It involves a reciprocal cosine. Therefore, we start this off by saying r as a function of theta, 0.5 over cosine of theta, but 1 over cosine of theta is the secant of theta. So r is equal to 0.5 times the secant of theta. Now, r dot, which is, and let's back out on this a little bit, r dot equals dr dt, the derivative with respect to time. But that is equal to dr d theta dt. And so we're going to use this idea to get r dot. So the derivative of r with respect to theta would be 0.5 times the derivative of the secant. So dr d theta is 0.5, and the derivative of the secant is the secant tangent. So dr d theta is 0.5 secant tangent, but d theta dt is theta dot. That's where the theta dot comes from. So this piece, dr d theta. This piece, d theta dt. Multiply them together, we get r dot. That's usually the easy one. The next one is harder. Why? Because we have three different terms that involve theta, and which means we're going to have to use the product rule, and we're going to get three different terms out of the derivative. Term 1, term 2, term 3, all of those terms added together. And so the product rule says, first of all, go in any order you want, but let's first take the derivative of just the theta dot piece while holding everything else constant. Then we could take the derivative of the secant piece while holding everything else constant. And then we could take the derivative of the tangent piece while holding everything else constant. And I need to pause just a second and remind myself of what these derivatives are. And the derivative of the secant is secant tangent. So when we get here, the derivative of the secant is the secant tangent. We've already used that one. And the derivative of the tangent, I need to, and I think it's secant squared, but I'm going to look that one up real quick. Derivative of the tangent is secant squared. Okay? So we'll use that. First term, taking the derivative of theta dot, simply gives us theta double dot times all this other stuff. The second term, we'll take the derivative of the secant, which is the secant tangent. So we'll transform that into a secant tangent. Everything else stays the same. Okay, let me see. Is that what we did? No, it looks like we took derivative of tangent next, because the derivative of the tangent is secant squared times the secant gives us the secant cubed term. We went out of order. This is the derivative of the tangent piece while holding everything else constant. And then finally this piece will come from taking the derivative with respect to this of the secant while holding the 0.5 theta dot tangent. So we'll have a 0.5 theta dot. There's one tangent in there. The derivative of the secant is the secant tangent. So we're going to have a secant tangent tangent. We're going to have a secant tangent squared out of this still, and then we're going to have, after taking the derivative of the secant, we're going to get an extra theta dot out of that, so we're going to have a theta dot squared. Okay? Practice that. Finally, knowing r dot, and r double dot, and they gave us information about theta, theta dot, and theta double dot. What did they give us? They said theta is 30 degrees, although we need to convert that into radians. Theta dot is 2 radians per second, constant. Therefore, theta double dot is 0. Taking these numbers and plugging them numerically into here, which means I'll plug in a theta double dot, I'll plug in a theta, I'll plug in a theta dot, and I'll plug in some theta dots and some thetas. I got a lot to plug in, but when I plug in these numbers, I'm going to get r is equal to 0.5774. I will get r dot is equal to that, and I'll get r double dot is equal to that. Check it out. Make sure you agree with it. At this point, we've done the hardest part of a Chapter 12 problem, and it's nothing but a Chapter 12 problem. The final easy part of the Chapter 12 problem is simply take these 6 numbers, theta, theta double dot, theta dot, theta double dot, r dot, r double dot, take those 6 numbers, plug them into the 2 acceleration pieces, and so we know r dot, that's a number. We know theta dot, that's a number, we can square it. We know r, that's a number. Plug in the numbers and we know a sub r and we know a theta. Where's the value in that? Because we're going to say sum of forces in the radial direction is equal to mass times the acceleration in the radial direction, and we're going to know that number. Therefore, what we'll solve for is any unknown forces. Chances are this will be 2 equations, 2 unknowns, because our other equation will be sum of forces in the theta direction equal mass times acceleration in the theta direction, and we know that number. So what we'll be able to solve for is unknown forces. Let's simply recall that we know those numbers. So the final piece of this, let's keep the free body handy. Sum of forces in the radial direction, mass times acceleration in the radial. We have in the radial direction, and I want to highlight that unit vector, E sub r. We'll highlight that. We will have a component of the normal, okay, and that will be normal times the cosine of this angle theta, which is 30 degrees. And then we will, what do we have in the gravity direction? We have a slight negative piece acting in the gravity, and where gravity contributes to the radial direction. So it's going to be a negative mg sine of that 30 degrees is equal to mass, which is 0.5, times the radial acceleration that we got from the other page. I was wrong. This isn't a 2 equation, 2 unknown problem, because the force between the fork and the ball does not show up in the radial equation because they're perpendicular. So that means the normal is the only unknown, and the normal is 3.72 newtons. 3.72 newtons. Now we'll sum forces in the theta direction, and looking at our free body diagram briefly, the theta direction is that way. So this force is 100% in the positive theta direction. Gravity has a negative piece in the theta direction, and the normal force has a negative piece in the theta direction. And so what we're going to get out of this is 100% of positive F in the theta direction minus a normal piece sine of 30 degrees minus a gravity piece cosine of 30 degrees. Check the free body diagram yourself to see if those angles and the sines and cosines are right, and they are, is equal to mass times acceleration in the theta direction. We learned that from the Chapter 12 part of the problem. The unknowns in here is merely F, because we know the value of the normal force. We can plug in that number. This is the only unknown. Solve for it is 7.4 newtons. Okay, so in summary, a big old Chapter 12 problem. Every bit of this from here all the way down to here is a Chapter 12 problem, and it required taking what I sometimes call the funny derivatives, which is really product rule and chain rules. Okay, writing r and its derivatives in terms of theta and its derivatives. A great Chapter 12 problem. And that ends this video.